part 2. Okay. So at this point about logs, we should have learned between Algebra 2, previous lessons, just coming all together, that in other words, the log y is the exponent to which b, the base, must be raised to get your answer, right? We've also learned that a log function is the inverse of an exponential function, correct? We've also learned that log with a base of 10 is called your common log. You all remember that from Algebra 2. And then a log with a base of e is called your natural log. It's written on the paper. Just read it since you were talking while I was teaching. Is base the subscript part or the huh? The base, your B? Yeah, it's the tiny, yeah, the subscript. Your base. Now we're just gonna go over like putting it together as far as transformations, what it looks like, and be comfortable. Just like we do with exponentials, we wrote it in its transformation form. We're gonna write log in its transformation form. Okay. So up first, the parent function that we're gonna be using is just a general parent function, which is y equals log base b of x. And that's because b can be anything but negative and 1. Or 0. Of 0, but 0. Okay, so up first, if I want it, let me know when you want me to teach. Like, seriously. I know you may not care about your grade, but there are people who want to learn. Take a nap. Do something else besides interrupt other people's learning. We're in this class entirely too long today for me to sit here and suck it up. And I shouldn't have to. And it's recorded, so I don't care. You can say why I told it all. So here we go. Vertical dilation. When you have a vertical dilation, that is combining stretching and compression. Okay, because in geometry, you learned that a dilation means that it's either getting big or getting small. Do you remember that? So instead of having it separate, we're just going to write vertical dilation. And so that is going to be written as y equals a log bx. Okay. Note to self, if a is greater than 1, then that is a stretch. If a is between 0 and 1, then that is a compression or shrink, whichever way you want to call it. Got it? They're okay if you just say a dilation by half or dilation by 1. So if you don't want to have to remember whether it's a stretch or compression, writing dilation is acceptable. Okay? Reflection in the x-axis. If it's a reflection in the x-axis, meaning that you're going to reflect over the x-axis, that means your A is negative. Okay, a reflection in the y-axis. Because B stands for base for log and exponentials, instead of using A and B, they typically use A and C so that there's no confusion. So if we have y equals, you're going to have log base B, and it's going to be a negative CX. So a negative number times X is going to cause it to reflect over the y-axis. Okay, your translations that shall stay the same and be the same. That's your H and your K, right? And we remember that X's are. So we have y equals log base B of X minus H plus K. Okay, for a log function, your H is going to always be your vertical asymptote. So when you put all variables in place, and let's just say you have big bama mamma jamma of a transformation take place, it would look like this. Y equals A log base B parentheses C parentheses X minus H plus K. C could be positive. Okay. The key thing to notice here is that if there is a number in front of X, it has to be factored out. Otherwise, you will not know your real H. That's why it's double parentheses. All right. I don't know. I'm supposed to teach it, so I taught it. I mean, you had it in algebra too. So we're doing it right now. How is it just C? Because it can be positive. It's if it's negative, that's why it's reflected over the y-axis. Oh, it's a horizontal dilation. I don't know why it's not on the notes. Yeah, so I don't even know where to write it. I just realized that they don't talk about the horizontal dilation. Yeah. If you want to write horizontal, I don't even know where to write on mine.
Just write it right there.
A horizontal dilation. So if you have a horizontal dilation, it's going to be y log base b with a cx. Okay, your x is a liar though. So when c is greater than 1, it's actually a compression. And when c is between 0 and 1, it's a stretch. But again, you could just say dilation to describe the transformation. Mm-hmm. All right. Are you ready to apply the transformation rules? Here we go. So up first, we have h of x, and h of x equals 3 plus log x. What variable am I given? Well, yeah. Sorry, what transformation one? A, C, H, or K? We're given our K. So we know that K equals 3. Okay? Because K equals 3, there are rules that we're going to follow. So we're going to write out the rule. So the rule to our x's and y's. How are our x's and y's changing? Is our x changing? But our y's. So our x's are going to stay the same, but to all of our y's, we're going to add 3. Does that make sense? So on the table or the graph, I would just be adding 3 to all of my y's. Okay? But in words and description, what is happening to the function? There we go. So we're taking g of x, which is our parent function, and we're shifting it 3 units. So g of x is translated or shifted up, however you want to write it. It's translated 3 units up. I think if you say shifted and then up. Yeah. Because it was outside of the function? Because it's outside of the function? It's my K? I don't know how to answer it other than saying where it's located. So if I have a change outside of the function, this right here, it's your K. If anything's being added or subtracted, no, it told me. It says right here, you're using f of x as natural log of x and g of x as log. So what happens to them? So log of x is g of x, right? So I'm taking g of x and I'm translating it 3 units up. Okay. All right. Here, we're going to state what's given to us, what transformation variables are given. H, yes, but not K. A. We get A, and we know that A is a -2. And we're given our H, and H is 3. Okay? So mathematically, what's happening to the points on my table and my graph? What is the rule That's going to affect X's and Y's. So what's happening to X? Right, 3. So to all of my X values, I am plus 3. I didn't mean to put a comma. I'm going to parenthesis. I'm going to put a comma. What's happening to my Y's? And then all of my Y values are being doubled, right? -2 times Y. Those are the rules that are taking place to each one. You honestly not see it's the same thing from exponential?
The only thing is I
I was like,
I feel like the thing that they're trying to do is switching G of X or what?
it's just saying that's what you're going to write is the description. So what is happening to f of x? F of x is what? There we go. So f of x is, I'm going to write it as a dilation instead of stretch, is dilated by 2 reflected over the x-axis. And what? What's the last thing? And shift right 3 units. Okay. Yes. We're good.
Wait, Miss Jones, what is the difference between dilation and stretch?
Nothing. I said that earlier. I said dilation is altogether a stretch and a compression. Because dilation means you either get big or you get small. All right. So last one. So the last one here. Before you do anything, what's happening?
Being reflected with the y-axis.
Good job.
Dilation. Is dilation. Because the 2, right? The 2 is usually the X with the big.
Oh.
Oh, it's being added. It's being left 2.
There we go. We're gonna rewrite it.
It's like, oh, it's multiplication of the friend.
Nope. All right, so we're gonna rewrite it so that it's in the standard transformation form. So this is actually y equals log base 3. And you're gonna have a negative, because I'm gonna factor out the negative, because x needs to be positive and by itself. And when I factor out a negative, I'm left with a positive x and a -2. Does that make sense? It is.
Oh, yeah.
Yeah. That's why you have to rewrite it in order to follow the transformation rule. I know. That's why I put this.
Like -x plus 2.
But you would have to factor out that negative to know the real transformation.
We just like know it's left 2. If you have -x plus 2. Yeah, because it's just like I look at that and I'm like, oh, that's left 2.
I get what you're saying, but it was shifted to the right and then reflected.
Oh, yeah, that's.
I get what you're saying, but it was shifted, then reflected, which made it appear like you had went to the left. Does that make sense? All right. So what are we doing here? It's not left, it's right. Yes. So our rule, what's happening to our X's and Y's on our table? Are we doing anything to Y? No, there's nothing outside of the function, right? So for X, it's going to become negative, and then you're going to add 2 to each one. That's because we have a C value. C is -1. And we have an H value, and H equals +2.
We're about like if there's a log base now, it's not just.
We're just describing this. We're gonna write it out correctly. So you have a negative, right? I'm listening. Oh, your do now was for exponential, and we did exponential already. Yeah, your do now was 2 to the x. Yeah. Uh-huh. Your do not was 2 to the x. All right, so here we go. So what this one, notice that this is log base 3. Does that apply to f of x or to g of x? No. So what we transformed was log base 3. So when we write this, we're writing that log base 3 of x, that's the function, y equals log base 3 of x is translated or shifted, whichever word you want to use. It's translated 2 units right and reflected over the y-axis. Yes. Okay. Everything about your x is done backwards. So you're going to describe your left and right motion before you describe reflections and dilations. Is how I was taught to do it, you know. So everything about x's are backwards. Yes. All right. So what you're going to do is you're going to practice describing the transformation, drawing the transformation, and then stating the attributes. Okay. So that's for A, B, and C of example A. So again, I'm going to give you, let's say 5 minutes, 6 minutes. Just right at the top. Yeah. So like here, I would write my H equals -2. So it's going to be shifts 2 units left. Does that make sense? Okay. And then you're going to draw your sketch, identify the attributes. All right. As you're doing it, let me know if you need me. And then we will check and move on from there. All right. Let's see how we did. Are we ready? So for up first, natural log x plus 2, we already determined the shift. What did your graph turn out to be? Let's see. Let's see. Okay. You should have stated that your your vertical asymptote is now at x equals -2. And your y-intercept shifted from 1, 0 to -1, 0. Notice here that your 1, 2. What do you mean? What did I do wrong? Because -2, 0 as an asymptote, I can't go there. Remember, all initial intercepts start at 1, 0. And if I'm taking 1 and shifting it 2 units to the left, that puts me at -1. All right, your y-intercept. Now, for your y-intercept, so for y-intercept, notice I just wrote 0 of natural log of 2. And that's because if I plug in 0, I'm just going to be left with natural log of 2. And if it's on the non-calculator side, will I be able to write that value of natural log? No. So that's all you could do, would be able to state that it's at natural log of 2. Okay. Your concavity, it's obviously concave down. So our rate of change is decreasing. It's positive but decreasing. On the left in behavior, so on your left, as you're approaching, well, you can't go past -2, right? So as you're approaching -2, your g of x is going to -infinity. As you're going to positive infinity, x goes positive infinity, your g of x is going to infinity. So that's what your A should have looked like. Your B, you should have had a shift 1 unit up. Okay, so you're shifting 1 unit up. And these are the attributes that you should have had.
Over the one in the graph.
1, 1. Sorry. It should be at 1, 1. So we were at 1, 0. We go up 1. We're now at 1, 1. So the reason why it's at 0.1 is because you're asking yourself, for what did I have right part? Exponential. So think about the powers of 10. You're gonna think about the powers of 10. So if I had 10 to the it's a log base 10, exactly. So you're thinking of powers of 10. So when you have the power of 10, so 10 to the 1. 10 to the 1 is 10. 10 to the 2 is 100. But when you go the other way, 10 to the negative 1 is 1. 10 to the 100 is 1/100, right? So if I'm asking you for our initial, bye guys. If I'm asking you for the other point before 1, that point would have been at -1, and then it would have shifted up 1 unit. Does that make sense? Or do you see it as a graph? Yeah. Because it's better to look at it as the exponential inverse.
The intercept where it's intercepting